And coming up, we're going to start using these services to move. Actually, we moved some of these models before, right? Remember, we took was it the cube, and moved it around to hit the cylinder? Or we were rotating? Maybe you didn't remember that, but from the previous class, we have a few commands from raw services that moved the parts. So look back. Now, section 3.5 is going to introduce a controller, a PID controller. A PID controller to control the joint that exists between the two links. Yeah, a PID controller to do position control on the actuator, and then command that joint to a particular angle, and then move the two links. So that actually means that we need to start connecting the URDF with Gazebo with ROS control. So we'll have a brief introduction to ROS control here today. So ROS and Gazebo work together to command the joint with reference angles. And we're also going to be able to read the displacement, the joint displacement, through an encoder. My friend, what is an encoder? Don't, huh? Okay. Someone else, right here. What's your name, my friend?
Sali. We take the projector.
Sali, what's an encoder? It's right here, encoder. No? Very good. It's a sensor that tells us the position or the joint angle displacement, 0. Pi divided by 2. Something like that. It tells us the angle, okay? So, by integrating the controller, we can command the arm and we can read the angle. Two things. So we're going to use code. Actually, the first thing we're going to do is show you some code that might be able to do this without ROS control. But this is not the best choice. It's going to be a little bit slower. Then we're going to use ROS control to do this. So you're going to be able to see how we do it both ways. Okay? In this demo code, we'll have a PD controller that is found in the control hardware normally. Yeah, we're going to actually simulate that with ROS control and Gazebo later. For example, if you use Baxter has a PD controller in the control boards inside the robot. You just tell Baxter, move to this angle, and it does. It has a built-in PD joint controller. So PD joint controllers normally are running at a very low level in the robot. Could be the UR5 or the E1. Yeah. You can always build another PID controller, PD controller on top of that one for a different purpose. But the robot itself will have a built-in PD controller at the very low level to control the joints. Here we're going to have a simulated PD controller. A little bit similar to what you did on homework 1. And then later we're going to use Gazebo plugin for controllers, so we don't do this manually. And this is going to be an example of what that plugin really does. But right now it's going to be slower because by doing this on the code, we have extra computation and bandwidth requirements. For example, serialization. What does serialization mean? When you publish a topic, you put data into the messages and then you publish them, right? That part there has some computation. Also slows you down. So this is extra compared to the plugin. And when you send the message over a ROS topic or a ROS service, there is some message latency. The message has to travel through the Wi-Fi or through the Ethernet cable. There's some latency there through the topics. Yeah. If it's on the same computer, and let me say that. And then the plugin doesn't have to do some of these things. It's a little bit faster. Right now we're sending things from the node to Gazebo, right? There's a communication route between the node and Gazebo. So this slows you down a little bit, very little, but it slows you down. When you use the plugin, it's faster because it doesn't do these things. Okay, let's look at this code. So it's in minimal joint controller, source. Yeah, you can use ROS-SED. I'll use Emacs directly here. Minimal joint controller.cpp. Okay. Some new headers that we haven't seen before. These are Gazebo messages. Get the state of the model. Yeah, where's the robot, things like that. Apply joint effort if we want to move an arm. Get joint properties. And then this one is very important. Sensor messages joint state. This message here helps us to know the state of a joint. If you don't know what it does, what can you do? You open a terminal, right? Let me do this, and you can say, what? Cross message, show what? Sensor messages, joint state. You're going to get the joint angle position of every joint. It's an array, so if you have 6 joints, you had 6 numbers, you get the joint angle velocity. And effort is something that can mean either force or torque. Why do we call it effort? Because we have 2 kinds of joints. What kind of joints can we have? Revolute and prismatic. Prismatic. If it's prismatic, it's linear, so you get a force. If it's revolute, you get a torque. So effort is a word that describes either one of these. Each joint has a string name, like shoulder 0, shoulder 1, elbow 0, elbow 1. And so these values correspond to the order of the names. Okay? And then you have your header. So that's what we're doing, okay, with sensor messages joint state. Here, we're going to have global parameters. Why are they global? They're at the top, yeah, above all functions, outside all functions. We're going to have a PID controller. So here's KP. Yeah, normally you're going to be a lot larger than KV. And then we need to say what's going to be the sampling rate for the controller. How often is this controller going to run? Right now, we're just saying 10 times per second. Okay? Then we have a saturation function. If you don't remember what saturation is, it means it's the limit of the actuator. We can have different kinds of saturations. We can have joint limit saturations. You can tell the robot, hey, move to back here, and then you can't move further. So you saturate the joint, but also it can be for the torque. The arm may need to apply more torque to carry a heavy object, but the motor cannot provide it. Yeah, it's not like it's infinitely powerful, right? It has a limit, and if you ask it to do more, it cannot. When it cannot do that, it saturates. Yeah. Let me skip this periodicity for now. And here we're going to have a command, position command callback. Okay. And we'll get to that. Let's go to main maybe first to see how this is working. Initialize the node, have node handle. We create a variable for duration of 0.5 seconds. We have this function called test services. This is just saying, let's make sure services are available before attempting to process anything else, right? We can go find it, test services. Okay, and the way we do this is always, this is one way to do it in C++. We use raw services and then the method called exists. It takes the service topic, in this case Gazebo apply join effort, yeah, and this is tell us if it's running, true. So if it's not running, we issue a warning, and then this returns false. Then we do it again, not just with join effort, but join properties. Yeah, and then we say services are ready. Okay, so we're just checking if services exist. Who's running the services? Gazebo is. Okay, you're running Gazebo, you're checking, is this happening? Now, why do we do spin once? Where these will serve for the callbacks to get some value that might be needed for those calls. And then we sleep half a second to give it some time. And then this is just to test. After we know that the service is running on Gazebo, we proceed to create our clients. Okay? So this is set the torque client. If we want to move the arm, then we can issue a torque. Yeah, this is going to be our object. We take the node handle and say service client. We give the type of the service topic, Gazebo messages, apply join effort. Then we give the service topic right here. Okay, so that creates our object, service client. We do the same thing for get joint state. Yeah, we have a different type and we have a different topic. Now that we have these two clients, the clients are used to do what? To make a call, right? And when we make a call, we send a service message with it. Remember that the service message has two sides, the request and the response. Yeah. So here for the set torque client, we need to issue an effort. We're going to command an effort to the joint. You should move with this kind of torque. And then when we send a torque to the joint, it's going to move. When it moves, we want to know the position. So we get the joint state through the service message. All right? So we create these as Gazebo messages right here. We also have 1, 2, 3, 4 publishers. Torque publisher, velocity publisher, position publisher, joint state publisher. And all of these, in the first three, we're going to send float 64s. And the last one, sensor messages joint state. Okay, these are our topics, joint torque, joint velocity, joint position. We have one subscriber, position subscriber, and this goes into the position command topic. And this has a callback. Tell us the position. So what we're doing here is actually we're going to communicate with Gazebo in two ways. One way is through services. Another way is through topics. For these messages, we're going to have these types, torque message, position message, which is Q1. Q's are normally used to describe joint angles. And then Q1 dot is the velocity, the joint angle velocity message. Okay, these are part of what we're going to send out in the topics. Then we have local versions of that, Q1, Q1 dot, Q1 error, because we need a controller, yeah, and torque command. We have joint state message, we have a duration of 0.01 seconds, and the rate is 1 over that. Okay, so now we go back to the service messages to fill them up. Here we created these. Now we're going to start filling them up. So we have effort command service message, the request part, and then we need to give a joint name, and we're going to say we're going to work on joint 1. We only have one joint in this model. And then we're going to set, let's set the effort to 0. So this is just local. Nothing happens. And then do that for this duration. Yeah, that we set above, 0.5 seconds, I believe. And then for the joint states, the request is also joint name. And then we go to the messages we'll use in the topics. Here's joint state message, header, stamp, time now. And then we need a name. The name is the name of the joint. It can be a vector, so we can use pushback, but we push back a string. We only have one. And we set the position and the velocity to 0. Now, we're going to go into the while loop, and this is where we have the controller. Okay, see how this works. The very first thing that we do is we're going to issue a service call from the get joint state client. And we send this message that we created above. Yeah? And so it's going to return the response. It's going to return the response. We can get that right immediately. Get joint state service message dot response dot position. Here the 0 is redundant because we only have one. So you can, I believe you can do this without the 0 here. And we save that to Q1. And then we're just going to, just to show you that you can do this, we're going to republish this onto a topic. So you take Q1, you take Q1 message.data, this is just a number, you save it here, and then you take that to the position publisher, say publish, and send it in. So you get it and you send it back. What's my angle? And send it back. Yeah, so here, Gazebo is not going to do anything. We're going to do the same thing with the angular velocity, Q1 dot. You get, in the response, you're also going to get that thing, rate 0 here. That's the velocity, and then you save it back into Q1.message, and then you take the velocity publisher to publish that. Okay, now, right here we're getting the state through the service call. Now we can get the state, we're going to publish the states through the topic. So we have Q1, and we have Q1 dot. We save that to joint state message position, joint state message velocity, and then you publish. Right now we're just showing you a few different ways to send things to Gazebo. Okay? Now let's look at the controller. Here you want to compute the joint angle error. How do you do that? Well, you have a goal position command, something where you want to move. This command, I think, is at the top. Let me search for it. This one here. Right now is 0. Goal position command. Yeah? Let me see, 1 second. And the callback, we're going to get the latest position of the robot. The latest, the current position of the robot. But then we set that value to the goal. So maybe the robot is at 0. You get that position. And then you set the value 0 to the goal. So it's not moving. Yeah, it's not moving when this goal is 0. So here, this is the current position, and then Q1 is where the robot arm is. So the error here should be 0. This function is looking for something periodicity. You can look at that later, but we save the error here. And then this error is multiplied by Kp, and then we subtract the derivative of Q1 dot. Now these controllers, there's a bunch of different ways you can do this. Here we're not computing the error of the velocity, we just pass the derivative of the velocity. And then this is going to be a command. Okay? And that command is then set to this publisher. Guys, pay attention, there's a lot of detail and a lot of you are already lost, right? So, need to ask questions and focus. And then we publish this again. We can also send this through the service. We have the request and set the effort part of this request to torque command. Yeah. If you don't know what this looks like, remember you can say ROS SRV, show, gazebo messages, apply effort. Yeah, and then you can see the response and the request type for that service. And then we take that set torque client.call with that message and send it out. Here, if you want to make sure the service call was successful, you can look at response.success, save it here, and then use a test. If the result was not successful, make a warning. We have a subscriber and the position command. So we want to spin once. Get the position for the subscriber, run the while loop again, get the subscription, get the position from the subscriber, run the loop again, get the position from the subscriber, run the loop again. That's what spin once is doing. Get one message, try again. Get one message, try again. Okay, and then we have sleep. All right. So we examine the code. This is a summary. And let's then do some manual steps to understand more how Gazebo works, how the code works, and then we'll run it in a second. So here, it's important for you to learn the joint properties in our 2 degree of freedom simulation. Let's do that through the service. We can call Gazebo's get joint properties service, but we need to provide the name. And what this does is, this service actually is being constantly called in the control loop to get the position and the velocity in the code. Okay, don't get lost. We are controlling the joint, right?
Yes.
And we want to get the position of the joint angle position, and the joint angle velocity. Okay, so here is Gazebo. It's there, right? And then we want to do this service call. So you can say raw service call, Gazebo, get, joint properties. But then we need the joint name. Joint 1, yeah, like this. And so it says the type of joint that it is, revolute, no damping, the position is 0, the angular velocity is 0. I can successfully get this information, and then the message got the properties. Okay? So that's what we're doing inside the code. We can also issue joint torque commands using the apply joint effort service with joint name. First, let's get some information about this. Raw service info, Gazebo, apply joint effort. So this says actually the service that is running this is Gazebo, and it uses a type of Gazebo messages apply joint effort. Okay, it needs a joint name, it needs an effort, it needs a start time, and it needs a duration. This thing needs 4 things. Here we can also say raw service show Gazebo messages apply joint effort. Okay, so here's the name, here's the effort, here's the start time, here's the duration, and it'll say whether or not it succeeded.
Success is the request or the response.
You tell me.
I think it's the response.
It's always a response. Request is the first.
Sometimes I read the book, it's the request. I think the sequence of the request and the response can be changed.
No, it's fixed.
It's fixed.
You always have request first, and then you have response. Never changes. Yeah. So in the PD control loop, we're passing a joint torque update to the effort field of the effort command service message. Okay? We're doing that in a while loop all the time. Sending a new torque command. Go here, go here, go here, go here, go here. Whatever that is. So now what we're going to do right now is manually send a command message to the torque of the joint to move it. Okay? We can do that. This is not a torque. Now we're gonna show you how to send a desired angle manually. Okay. So we're gonna say Rust topic pub position command. That's the topic. Standard messages, float 64 1.0. Okay. Later in the program. I think we haven't run the code yet, so this is not going to work if we do this right now. We haven't started the node. What we're going to do is also examine the dynamic response. Do you remember what dynamic response means? Well, the answer is right there. We want to know how the position changes, how the velocity changes, and how the torque changes for that joint. How do we do that? RQT plot. It's going to help us plot data from any topic. So we're going to be able to say RQT plot all of these guys. But remember that these are ROS standard messages. So they have the data element. We don't just look at the joint position topic, because that topic has a data element inside. Joint position data, joint velocity data, joint torque data. Okay, so let me see. I think we need to start this node. Yeah. Let me see this topic list. Let's run. I forgot to include this command in our slides. Minimal joint bus run minimal. Yeah, so I started that node. Okay. Now we need to publish the topic. Oh, before we do that, let's do RQT plot. So you can say RQT plot now, and actually let's do a ROS topic list so you can see them. ROS topic list. So here's joint position, joint torque, joint velocity, right? It's waiting. So we say ROS RQT plot, joint position data, joint velocity data, joint torque data. We're going to wait for a second. So here's our curve. Nothing is changing right now. Right? So we put this here. Actually, let me put it here. And then we open one new window, and then we're going to do the ROS topic pub. ROS topic pub position command, standard messages float 64 1.0. We can just say 1.0 here. Yeah. That's the dynamic response, okay? And actually, if we pause this and we maximize this, you can see that the joint position is the blue line. You can see how it goes up, right? It's not, well, it has a smooth response here, and then the velocity goes up, and then it needs to slow down again as it's arriving, and the torque goes up very much so, and then you need to stop so it goes the other way, and then stabilizes at this level. This is the torque that you need to maintain that position, and it needs to work against gravity. So it's not free. When you do this, there's a muscle working there to keep the position. Yeah, it's a torque that you need to keep for that position. So it's very nice, right? You have the node listening for topics. That comes in, goes into the controller. It does a error computation. It updates the torque command. Yeah. It computes the torque command, and then it begins to move the arm by sending the effort. This would be great for you guys to go back and use GDB on this with Emacs or any IDE you want to use, and go line by line after you publish the command. Yeah, to see how this is working. So we do that, you get something like this, right? Now, we want to now also study contact dynamics. What if I hit something? What if there's an obstacle? We're going to hit a table in a second. So right now, we're going to manually insert a coffee table under the robot using the insert menu. And then we're going to do the same thing and study the response. So let's, actually let me go back to this window and go back to Gazebo. And let me publish again, but with 0 as a position. Now, let's move this a little bit, and let's say insert. Actually, it's here. Let's look for a coffee table. Yeah, put it right here. So it should be able to hit it. We take RQT plot. Maybe we'll put it down here. Play it. Yeah, it's everything is normal again. And then send this again. See if it hits. Oh, that's okay. That's okay. Let's see if we can do. Okay, there it is. So, for example, we can zoom in on this. Yeah, and for the position, it never reached 2 here, right? Never reached 2. I was unable to do that. The velocity was cut off very quickly. Didn't have a chance to slow down like it did before. And then the joint torque, well, had a big strike here when it struck the coffee table. Yeah. So that's the dynamic response. You need to make sense of these responses from the physical events.